In our last class, we learned how to solve exponential equations using common logarithms, or logarithms with base 10. Today we're going to be learning how to use the natural logarithm, or ln of x. The key to this is to remember that ln of e is always equal to 1. In other words, we're working with logarithms base e. Now, the formula for converting logs to natural logs is basically the same change of base formula we had before. If we are looking at the log base b of a, it's the same as ln of a over ln of b. This is just a different function on your calculator. You have an ln key as well. So for example, if we were working with log base 5 of 291, what we would type in is ln of 291 over ln of 5, and the result on our calculator is 3.5250. At this time, use the change of base formula to change number 9 and number 10 into natural logarithms. Then check your answers. The solution for the log base 5 of 132 was 3.0339, and the solution for the log base 3 of 64 was 3.7856. Now, what do you do when you know the natural log, but you don't know what x is? Well, you simply use the inverse function on your calculator, or e to the x, which is second and ln. So, it would actually look like this in notation: anti-ln of ln of x equals anti-ln of 0.723, or your result would be x is approximately 2.0606. Now, pause the podcast and try the next two problems. Again, you need to isolate the natural log before you do the anti-log. As you're checking your solutions, notice that I use different notation on the two problems. They mean the same thing. The anti-log of the natural log is just e to the natural log of x. The e and the natural log are inverses, therefore they cancel each other out. Both of those are acceptable notations. You will probably see both of them in your future. Now, to solve an equation with natural logarithm, it works exactly the same as it did with the log base 10. We are using this to solve an exponential equation. So, for example, if we have 5 to the 2x equals 7 to the x plus 1, instead of taking the common log of both sides, what we'll do is we'll take the natural log of both sides. So then we have ln of 5 to the 2x power equals ln of 7 to the x plus 1 power. At that point, we're going to use the power rule to drop the exponents in front so that we can eliminate our exponents, and we end up with 2x ln 5 equals x plus 1 ln 7. Now, because we have variables on both sides of the equation, we do want to use the distributive property. So our next line would be 2x ln 5 equals x ln 7 plus ln 7. Now, we're going to continue the problem by moving like terms to the same side of the equation. So I'm going to subtract x ln 7 from both sides, and I end up with 2x times the natural log of 5 minus x times the natural log of 7 equals the natural log of 7. Factor out the x. So I have x times 2 times the natural log of 5 minus the natural log of 7 equals the natural log of 7. At this point, I will divide both sides by 2 natural log of 5 minus the natural log of 7. Be careful with your parentheses. Be sure you close the parentheses after the natural log of 7. Open a parentheses for the denominator. Close it after the natural log of 5. Close it after the natural log of 7, and close it at the end. And we end up with a result of approximately 1.5286. At this time, I would like you to do the remaining problems on the page and then check your work. As you check your work on these problems, there are a few things I would like to point out. On the first problem, notice after I used the power rule and dropped the 3x to the front, remember that the ln of 3 is actually the same as the number 1. So that was 3x times 1, so I just wrote on the next line down 3x. I did the same thing on each of the successive problems. Now notice on the second problem, the blue problem, that the first thing I did was divide both sides by 5 because you do want to isolate e before you take the natural log of both sides. You can do it without it, but then it gets a little bit more complicated because you would actually have to go back and use the product rule, because then the natural log of 5e to the 5k would be the natural log of 5 plus the natural log of e to the 5k. It involves subtracting natural logs on both sides. It just messes it up and makes it ugly. On the next two problems, notice that the domain of the function, the domain of any logarithm, whether it's the natural logarithm or a common logarithm, is that x has to be greater than 0. You can't take an exponent of a positive number and get a negative answer. So on each of the solutions at the end, I did have to set the final solution as 0 is less than x is less than 1.3863. Had one of them ended up being, for example, on the second one, if it had ended up being t is greater than or equal to 48.5, I would not have needed to use the domain. Now do the word problem, and then we'll go to the example on the next page. In part A, all we had was a simple substitution and then use your calculator to get an answer of approximately 503.1 torrs. On part B, we actually had to solve the exponential equation, take the natural log of both sides, and solve it. We ended up with approximately 4.2 kilometers. This example is of an exponential function. You've been given actually an equation that determines the fraction of people who have heard the rumor at t equals 0, a constant, and so on. Now, in our example, in a study, sociologists determined that at time t equals 0, 5% of the people in the group have heard a certain rumor. After 2 days, 25% of the people in the group had heard the rumor. And the question is, how long will it take for 80% to hear the rumor? So let's start out with what we know. We know the fraction after 2 days. So the first thing I knew was that p was 25% when t was 2 days. And we knew we started with 5% at t equals 0. So substituting these numbers into the problem, I was able to figure out what the constant was because I couldn't solve it for 80% until I knew what k was. So I substituted the numbers into the problem. You can see the work as we go. On the first line, it was a straight substitution. Between the first line and the second line, from here to here, I did the distributive property. I distributed the negative 0.05 in the denominator. In the second line, all I did was combine like terms. I simplified the 1 minus 0.05. On the next line, what I did was I multiplied to eliminate the fraction. On my next line down, I distributed again. To get the next line, what I did was I subtracted 0.0125 e to the 2k on both sides. So I was isolating my variable. On the next line down, I, again, was working on isolating my variable, so I divided by 0.0375. Then, because I had e isolated, I took the natural log of both sides right here, did the power rule. I knew that ln e was equal to the number 1, so I just had 2k equaled that natural log, and that helped me come up with a value for k. That was the first half of the problem. Then, to solve the second half, I simply resolved it again, only this time I didn't know t, but I did know 80% for p. 5% did not change. The only thing that really changed is now I know the value for k, which was 0.9229. As I did the work, I followed the exact same steps. I distributed, I simplified, I multiplied, I distributed, I isolated again, I took the natural log of both sides, power rule, natural log of e was 1, solved the resulting equation, and came up with approximately 4.7 days. This concludes today's podcast.